Welcome back, ladies and gentlemen, where facts absolutely care nothing, zero, about your feelings. So what we're going to do now is I'm going to show you the algebraic version of the wave function, and this is really important. It tells you two very interesting things. With the algebraic version of the wave function, it tells you that you can quantize the movement of the particle. But it's also important because using that you can then solve even more unknown properties, because you have now more knowns, right? So if you have, for example, I've said this before, but let's say I went to America and I met a Republican. Quantize. In other words, you can make them into bits, into like pixels, right? Which is what's actually happening, right? It's not really a wave function. Well, okay, it's both, right? You know the wave-particle duality? So you can use both. So, So, for example, I went to America and I met a Republican. Okay, that doesn't really help me. That means I met half the country. It could have been someone from half the country. Right? What else can you tell me about the person? A tiny tetrahedron. What else can you tell me about the person? They were they had olive skin. Okay, I met a Republican with olive skin. So now that's two things, which helps you eliminate even more people, so it narrows down your search. So that's basically why it's important to know the algebraic method and the calculus representation of the wave function. And now I'm going to show it to you. And then we're going to show you how we can use that to figure out the possible energy levels of a particle. Because if you remember I told you at the beginning that with quantum particles, they can only exist at certain levels, just like the light in a traffic light. So, you know, the traffic light, you have green, then it goes up to orange, goes up to red. It doesn't go in between. And speaking of traffic lights, here comes Ernie Banks. All right, so I am going to show you what I'm actually talking about. Here is the original wave function, if you guys remember, the Schrodinger wave equation. The Schrodinger wave equation, if I can get this to focus, right? Where are we? Okay, so it is this. It is I by h bar, okay? And then the derivative, partial derivative of the wave function with respect to, I'm pretty sure it's t, if I can remember correctly. Yep, t. Okay, that means that we're only deriving it in terms of time. So that's basically the average speed in a way, if that makes any sense. It's not really true, but it's something similar to that. Equals negative h bar, all right, squared over 2 times the mass of the particle, multiplied by the second derivative of the wave function in the spatial direction. All right, that's the second derivative of the wave function in the spatial direction. Okay, plus the energy of the function. All right, so that's v of psi. Okay, so that is the original quantum one. We've done this before. Now what we're going to do is we're going to change this to the algebraic method. Right, so we know that d psi, so d psi dt, which is the what we said about speed. I did this last time. All right, d psi dt equals negative I, which is just, you know, that's that multi-dimensional number, that complex number, right, multiplied by a, which is that little constant which talks about the, you know, the, what do you call it, the angular velocity of the particle, like its orbit, you could say something like that, it's spinning on its axis, all right, multiplied by the wave function. All right, that is that, and all we've done is said we've converted this into algebra. So that up there, we put it into this. So now we're going to get the wave function using different letters. So it's like I said, you know, we're finding something using cross-referencing, I guess you could call it, right? All right, next, let's do it. We've got d phi dx, I keep calling it phi, sorry. d psi dx, that means the derivative of the wave function in the spatial direction, and that equals negative 2 times a, which is at orbit speed, I guess, the rotation on its axis speed, I guess you could call it, which is very, very inaccurate description, but it's good enough for now. And mass by the distance away by its location, basically, over h bar, which is, remember, that's the pixels, right? As Dome Father likes to say, the tetrahedron pixel. All right, over h bar psi. All right, and psi is once again the wave function. Okay, so all that means, stay tuned, the answer to everything is in the final step. That goes to that. Okay, so all we've done, we're just doing some translation. We're converting this into algebra. In other words, we're going from Newtonian mathematics into Arabic. Because algebra, as you guys might know, comes from Algebr. It's an Arabic word. Yes, the Arabs actually created algebra. But that was before their decline, when the... we won't get into politics. All right. So the next one is the second derivative. So if we derive this again, all right, we're going to get that over that, and that now looks like that. All right, that's now again in the space direction. We're now deriving again. All right, and I don't know if you guys remember what derivatives are, but if you don't, go back. I'm really going to do a basic entry calculus course. I'm pretty sure I'm going to do that for you guys once I finish my my subjects. All right, we've got that, and that equals this. It equals negative 2am over h. Always reminds me of ham every time I see that. I don't know why. Outside of psi plus x, which is the location of the particle, right? D psi dx, which is a derivative in the x direction. All right, so now it's still got a bit of calculus in there, but we've added heaps of algebra, which makes life much, much easier. Oh, the wind keeps blowing my stuff. Maybe I should do this inside. Alrighty. And then, right, all we have to do is plug all of these into here. So as you can see, that, right, is down here. So that is down here, which gives us that. We can now put that in that's place. So we can say, you know, there's this, I don't know, fun guy. You know, who's fun guy? Well, we know it's a male and it's someone who uses periscopes. So that's two pieces of information. That's the first piece. We've now swapped it for the second piece, right? And then here, right, this, we put that in there, okay? And then it becomes basically an algebraic equation, which becomes back to high school mathematics. Now, the algebra is a bit messy, but in the end, once you solve that, you can actually solve it and get V, which is the potential energy of the particle, which is brilliant. Now, once you solve all of this, which I did last night, here's one I prepared earlier, you get V of x equals 2 by the mass, only for this particular equation, a squared x squared. All right. Now, what does that mean? And this is the part that's quite fascinating, right? Here was the equation. Remember, we just did it for you on the last lecture. How can I go finish programming my content? Right? If you remember, that was the wave function, right? That was the wave function of this particular particle. The particle moves in such a way that it makes this pattern, and that's the pattern, right? What happens is we get the energy is this. That means, and this is the really cool part, this means that the energy of the particle can only be, right, at a level that is equal to a multiple of this. So 2 times the mass by the orbit spin squared by the distance squared. Now that's really fascinating, because in real life, when you walk down the street, you don't have to only exist at certain parts of the street. Like, I can only exist outside the food store and the pharmacy. So if you're looking for Fancy Flock, you can only look for Fancy Flock outside the pharmacy or the delicatessen or the bakery. That's it. She'll never be outside the news agency. You know what I mean? It's exact, discrete sections of where you can find the person. And it's amazing, absolutely amazing, that these freak geniuses 100 years ago, pretty much, in 3 years it'll be around 100 years, they were able, or will I? You don't know. They were able to mathematically represent what, you know, that analogy about fancy flock with quantum particles, which is unbelievable, amazing. Absolutely amazing. All right, so that is the end of that, and that's it. That's all I got, man. I just want to show you guys the algebraic version. So just to recap what we did, we took the actual wave equation, right? I go sit in front of the bakery. That's it. Now I know where to find you. All right, so, I can smell that Arabic coffee. My dad made it. I've got to go have some. Definitely going to go have some. So we got that, right? So I by the pixel and the sort of like the speed of the particle, I guess, if you want to call it that. And then equals, and this is what Schrodinger came up with. Yeah, Dad. I'm coming down. I'll stop the lecture in a sec. I'm almost finished. Oh, all right. Oh, Mel brought me the coffee. You're a sweetheart. Oh, now I don't have to end the lecture. Thank you. Look at that, guys. Here we got some beautiful Arabic coffee, or Turkish coffee, or Armenian coffee, or Egyptian coffee, or Lebanese coffee, or Greek coffee, whatever you want to call it. So as we said, we're recapping here. We got that, right? We got the negative pixel squared over 2 times the mass and the second derivative in the space direction plus the potential energy, and we converted it. We said that the derivative time-wise of the wave function, so sort of like the speed, I guess, is negative I A psi. Cloud for drip rates. Ah, yes, that would have been fun. You would have done like logarithmic and exponential functions. That's sort of like, yeah, velocity equals mass squared and orbital speed squared. Of course, the Dome Father, as always. What's the formula for the coffee? You'll have to ask Honest Joe about that. We have the derivative in the x direction, and then we got the second derivative in the x direction, and then we chucked it all in, and we found out where the particle can exist. It can only have energies quantized at this level, and that's it. So now we're going to have the coffee, because facts don't care about your feelings, but my feelings care about coffee. Alrighty, that was it, my friends. I think I might go to the GoFundMe and talk to you guys while I have my coffee.